Record on this computer. Okay, so welcome to our Zoom class in computer, software engineering. And we're in the middle of the chapter on architecture. And we're talking about multi-tiered client-server architecture. In other words, not just, what does it mean multi-tiered? It means that you don't have just a server and the clients. You have a server who himself is talking to another server and then to another server. In other words, you'll have a database server, which will provide you your data, and then an application server, which will actually run the procedures on the database, and then the web service, which will communicate to the application server. In other words, there might be other things the application server does other than talk to the database. But all the functionality that you need for your website will be on this other server. And this will just be a conduit. That's like a tiered layer. You can think of this as layers, but it's not layers of software, it's layers of functionality, which are expressed by servers. There's different servers have different functionalities. So now we're going to talk about sort of a subcategory of client-server architecture, which is service-oriented architecture. You hear a lot about this, SOA. It's a buzzword nowadays. Service-oriented architecture. What is it? It's called SOA. What does it mean? Services in a service-oriented architecture are stateless components, which means that they can be replicated and can migrate from one computer to another. In other words, I may have services that I can I don't necessarily have to have them on one server. I can move them from server to server. Many servers may be involved in providing the services. In other words, I may have a pool of servers and each one provides a different service, and I sort of address the pool and get the service that I want. A service-oriented architecture is usually easier to scale on demand as demand increases, right? Scaling up is easier to do with scaling up. If you have, in other words, if any server can do anything, and we can we can decide at any moment how many servers we want to do this thing, to do this service or that service. So we're service oriented. In other words, we're just providing services for people who want services. An example of a service, well, we'll talk about microservices and then I'll give you an example. But a service can be DNS, can be any service that a server can provide. So now we have, like I said, there's a pool of servers. So who do we address? We address the pool, but how do you address the pool? Normally you address an individual server. So we need to have a service gateway. And I'll address all my service requests to the gateway, and he'll find the relevant server to give me the service. It could be that two of them give me that service and he'll choose one. So there'll be some kind of load balancing. So issues in architectural choice. So we saw a bunch of different architectures. Here are some issues in the choice. So if you are mostly using structured data that may be updated by different system features, it is usually best to have a single shared database that provides locking and transaction management. If the data is distributed across services, you need a way of keeping it consistent, and this adds overhead to your system. In other words, updates, whenever you have data and you're going to have multiple data servers that have repetitive data, you're going to have some kind of way of maintaining consistency between the databases, and that is going to add overhead. That's going to be an issue. It's going to be a difficulty you're going to have to deal with. Change frequency. If you anticipate that components of your system will be changed all the time, then making the component services is going to make things easier. In other words, instead of having, you think of services as functionality taken to the nth degree. In other words, not just that I have a function and another function. Function is essentially a service. I want this service, I go to this function. I want that service, I go to that function. That's all in the same process, or all in the same computer. But that simplifies things. But we can even make it more simplified and say, we're going to have different services that run on servers, and if I want to change the component, I'll just make, I know that I don't think the software is not even, it's totally different software. We'll just have a sort of a unified interface to servers, like for example, using JSON or XML. In other words, I'll send a message and I'll get back in JSON and get back a response in JSON. I don't care anything about how that server is doing its job. And therefore, if I want to change the component, it's easier. The system execution platform. If you plan to run your system on the cloud with users accessing it over the internet, it is usually best to implement as a service-oriented architecture because scaling the server is simpler. In other words, don't try to make a single machine that does everything for your website or for your software. Make different services that can be either on the same machine or on different machines. But view things in terms of services. What services do I want? If your product is a business system that runs on local servers, a multi-tiered architecture may be more appropriate. Right. In other words, if you're doing everything internal, then you don't need to have services. You don't need to. Why should your company be going out to the internet and then back again to itself? In other words, if everything is local to my company, then I may as well have everything on local servers. Although this less and less is the case nowadays. In other words, the problem with having local servers is that you need then, depends on the size of your company, but you'll need, systems administrators to run those servers and update those servers. You have all the overhead of managing servers, which is not a good idea, really, because you can't be experts in everything. You'd rather be experts in what your software is trying to do than in managing servers. So it's better to have it on, Amazon or Microsoft. Oh, what did I just do? Screen off. Okay, let's go on. So you're going to have to make technological choices about what type of database you want. Should you use a relational SQL database or an unstructured NoSQL database? In other words, an SQL database is going to be faster. Well, depends on the data. Sometimes in NoSQL, if it's a small database, it might be faster to use a NoSQL. These are decisions that you have to make. As you're all familiar with SQL, I don't know. Are you familiar with NoSQL?
No.
What, somebody? Somebody says
No,
yes.
I don't know what that is though.
No. Yeah, so you can think of it as just another kind of database structure that's not using SQL and that's more flat. Like, in other words, instead of tables, for example, just think of it like this. You could just have text files. Nowadays computers are fast. So what about just having a text file and searching your text file with grep? I don't know. I'm just saying, for example, there is something specifically called NoSQL, which you can look into. But the idea is that you don't have a whole distributed database structure like an SQL, and you have just files, just regular files. See, database files are usually binary. Anyway, it can sometimes be faster to use NoSQL. Platform. Should you deliver your product on a mobile app? Or a web platform? In other words, well, nowadays everybody, if your product is a web product, then it's going to be doing both, an app and a web platform. Server. Should you use dedicated in-house servers? Well, as we talked about before, or design your system to run on public cloud? Should you use Amazon, Google, Microsoft, or some other option? Now, these are decisions that you have to make. Nowadays, like I said before, nowadays almost everybody uses either Microsoft or Amazon Cloud. Google, I guess, also. Amazon actually is, Amazon basically is just a company that sells stuff on the internet, but in order to run their company, they had to pay a lot of servers. And therefore, they became experts in servers. And so then they said, well, we've got all these systems administrators, all these server farms. Why don't we make more money by also giving people the right to, renting out our servers? So nowadays, if you want to build a website, you basically rent a server from Amazon or Microsoft or Google and host it there. And then you don't have the overhead of having to maintain a server.
I ask a question on that?
Yeah.
I never really understood this. How do you rent a server? Is it like a physical thing that's somewhere else? Like, what does it mean to rent a server?
Well, what it is they have, my father used to say somewhere in Kentucky, they have, a server farm. And there's millions and millions of servers there. And those servers are actually like very powerful and with lots of memory. And when you go to Amazon, you can say, I want a server that's this and this memory and this disk size. And they'll create for you a virtual server, which will actually sit on one of these very powerful machines. But actually, there's no guarantee it'll stay on that machine. It could move around, and there could be many, many servers, quote unquote, servers on a particular machine. And you have to install, they give you, and you can ask for the server, and they'll give you an IP for the server, and they'll tell you how to access it. And you can ask for it to already come installed with Microsoft or with Unix, and you can ask for it blank, and you'll install everything. It's cheaper if you ask for it blank. And you can ask them to update it for you, or you can update it yourself. But the point is, everything is done remotely. Your access, because the server doesn't, you don't just see the server. It doesn't need to be in the same room with you. Once it's not in the same room with you, it may as well be in Kentucky. And the point is, it's a virtual server. It's not even physically locked to one machine. It can move from one, if they want to take down a machine because it's old and they want to put a new one in, they can move your server to a different machine and it'll be seamless. From your perspective, nothing happened. Does that answer your question? Or not enough?
I think so. I don't know.
Still not clear on it. Well, the truth is, you can only be clear on it if you actually create one yourself. In other words, you have to pay, $10 a month, then you get your server, and then you put on things, and you put a web page on it. It's a whole field. It's a field that used to be called systems administration, and now it's called more DevOps. That's the field, development operations. And because you're whatever, just really it's the same thing. You are not a programmer, you are a person who knows how to set up servers so that programmers can use those servers. Set up the environment, set up all the things, make everything nice and warm and fuzzy so that the programmers can do their work. Somebody has to do that. That's a different job. That's not a programmer. That's a systems person. What I would call a systems person, but now you call them like a DevOps person. If you ever watch the TV series, it's called Silicon Valley. There's a character on that who's a programmer, but he's also the server guy. Somebody has to be an expert in servers if you're going to make your own servers. Even if you're not going to make your own servers, you're supposed to be somewhat of an expert. You have to know how to use Amazon. Open source. Are there suitable open source components that you could incorporate in your product? Are you going to make everything yourself? Are you going to use open source? Or even another option is buy components. Development tools. You got to decide which development tools are you going to use. Are you going to use like Magenta? Is it or are you going to use Microsoft Visual Studios? Do your development tools embed architectural assumptions about software being developed that limit your? In other words, you got to choose a tool that's going to fit to the idea that you have beforehand, that you're going to do it on multiple servers or not on multiple servers. It has to fit to all the other decisions that you make. Okay. So here, there are two kinds of databases that are now commonly used. Relational databases, where the data is organized in structured tables. That's what you're familiar with. And then there's a NoSQL databases, in which the data has a more flexible user-defined organization. In other words, I would say more flexible. What does more flexible mean? You can do anything you want. Relational databases such as MySQL, right? MySQL is a free SQL server. What does it mean, a server? It means you install software called MySQL, and then you can access that machine remotely or locally and build tables and delete tables. They're particularly suitable for situations where you need transaction management. In other words, sales. things that are, or data that's being changed all the time. And the data structures are predictable and fairly simple. NoSQL databases such as MongoDB, so there's MongoDB, are more flexible and potentially more efficient than relational databases for data analysis. NoSQL databases allow data to be organized hierarchical rather than as flat tables. In other words, you can make a tree. Now, if you think about it, the tables in NoSQL, in MySQL are, there's no hierarchy, right? It's just like I have an index and then I can use that index to access another table. And all the tables are sort of like, spread out on the floor in my apartment. They're all there and I can access any one of them at any time. I don't access one via another. I mean, I may get a key from another one. I may go to one table to get the key for a third table. But there's no hierarchy. So NoSQLs allow for, don't have to be, but allow for a hierarchy rather than as flat tables. This allows for more efficient concurrent processing of big data. So so if you're doing big data, so if you have lots of data, it may be better to have NoSQL. But it's not so good for transaction. What do we mean by transaction? We don't just mean sales transactions. Transactions is a term in databases, right? You learned about that. Transactions means that you, basically, I think what it means is you put a timestamp on the, when you're doing a transaction, you sort of lock the data so that nobody else can do it. And then it's unlocked when you're finished. And that's called the transaction. I put in data and I take it out, and it sort of locks the database at that time. So we need that for anything that involves money or anything that's the data can't be, you don't want to be, very critical data, and that's being accessed all the time. Kind of like a semaphore, transactional. Delivery platform. What we mean by delivery platform is how are you going to deliver your service or updates, anything that any software you're going to deliver. It can be, wait a second. Yeah, delivery can be as web-based or a mobile product or both. Mobile issues. So in other words, if you're delivering a service or any kind of internet, thing, you might have if it's on mobile, if you're designing for mobile, you may have intermittent connectivity. So you have to be able to deal with that. You must be able to provide a limited service without network connectivity. In other words, there should be certain things that your software can do even when you have no connectivity, because the person may not have, you may want to be able to do certain things. Like if you have an audio reader, you may want to download some of the audio thing that you're listening to, their book that you're listening to, let's say, so you can listen even when you're disconnected. The software should be able to do that, or maybe for you. Or I can think of another example. In Zoom, sometimes the person has bad connectivity and then you don't hear him, and then all of a sudden you hear him and he's talking very fast. Why is that? Because his software detected that the connectivity was bad, and on his local machine he stored the speech that he created, and then he played it back faster so that you don't miss anything when the connectivity came back. So that's sort of like offline service that the software is providing. And that's even without a mobile. That's even on a desktop. Processor power. Mobile devices have less processor power, so you need to minimize computational intensive operations. Right. If your software is going to be on a platform that's mobile, so you don't have a full computer there. So don't try to do intense things. Power management. Don't try to use the mobile phone all the time. If somebody puts his app on your phone, if somebody downloads onto their own phone an app, and they find that their battery is all of a sudden being destroyed, is all of a sudden going down very quickly, it means that that app is overusing the processor and causing the battery to be worn down. So if you're going to design things for a mobile phone, you have to think about not overusing the processor. Maybe you want an on-screen keyboard. Of course, they're slow and prone to errors. You should design your program so that you can minimize the screen input and reduce user. To deal with these differences, you usually need a separate browser-based and mobile version of your product. As if you're in a browser, you can assume the person has a keyboard and he has access to all kinds of keys. But if he's on a mobile phone, you may want to have a different version of your software that is bigger buttons, fewer buttons. That's why sometimes there's certain features of software that you can't get unless you go to the website version, the browser-based version, because that's intentional. Because they tried to limit the clutter in their browser, in their mobile version. You may need a completely different decomposition. You may need a completely different decomposition architecture in these different versions to ensure that performance. And in other words, you may have completely different versions. You may just have a different front end, right? The front end would be the way it looks. You may have a different way it looks, but you may have to design the whole program differently so that it uses less power and can deal with intermittent connectivity and all those things. Of course, once you've designed it to work on a mobile, you'll end up saying, well, why not use that on the desktop too? Why do I want to use power if I don't need to? So depending on how good your app version is, you may just use your app version as your main version. We talked about this. You need to decide whether your server should be on the cloud or your own server. For consumer products that are not simple mobile apps, I think almost always makes sense to develop for the cloud. Okay, for business products, it is a more difficult decision. Some businesses are concerned about cloud security, and they don't want the services that they're using to be on the cloud. They don't want to store their data. The CIA doesn't want to store its data on an Amazon server, because then Amazon technicians have access to it. And well, maybe they have the password, but it's still more vulnerable than if it's in a vault in the CIA's own building. They may have a predictable pattern of system usage so that there is less need to design your system. Right. One of the reasons why people want to use the web servers is because you can, on the fly, increase the power of your server or increase the number of your servers. So if you have a fluctuating use, if you're a gambling site and whenever there's a football game, you have more people logging in than when there isn't, you don't want to keep all those servers. You don't want to pay Amazon. You can pay Amazon by the hour. You can tell them, turn these servers off now, and I'm not paying for it. And then I'll put them back on when I need them. So that's flexibility to cope with changes, which you don't have if you have your servers locally, because then you own the server, it's sitting there locally, you're paying for it all the time. In the sense, what do you mean paying for it? You have, instead of paying $10 a month, you pay $10,000 and you've got it now for 5 years. An important choice you have to make if you're running your software on the cloud is which provider to use. Okay, we said that. So now we're talking about open source. I guess I really already mentioned all these things. Open source is that you have stuff already done for you, right? You reuse rather than implementing new software, which reduces development costs. In other words, you may get things faster. The problem with it is that you are constrained by the software and have no control over its evolution. In other words, if you want a certain feature and you say, please add this feature to it, but nobody is interested in doing it, or the people who are running this, who own this, who are in charge of that open software don't want your feature in it, I think it's bad, then you're either stuck or you can add it yourself, I guess. You can modify an open source. The decision on the use of open source software also depends on the availability, maturity, continuing support of open source components. In other words, is it available and is it mature? Are there bugs in it still? Or is it pretty much been tested and used by a lot of people? And also, maybe it's going to be obsolete soon. Maybe people are going to stop supporting it. You don't want to start using something that's never going to change and never going to get new support, because you may need support for security, for new bugs that are found. Open source license issues may impose constraints on how you use the software. Sometimes if you use open source versions of things, then you're legally not allowed to sell the software that you make from it. So you may want to sell your software, but you may not want to sell your software. You may be just using their software to run a website. Your choice of open source software should depend on the type of product you're developing, your target market, and the expertise of your development team. Development tools. We mentioned this also. Development tools, technology such as mobile development toolkit or a web application framework influence the architecture of your software. Okay, the development technology that you use may also have indirect influence on the system architecture. Developers usually favor architectural choices that use familiar technologies they understand. For example, if your team has a lot of experience of a relational database, they may argue for this instead. Knows people maybe say, I don't want to learn Mongo. I don't want to use a NoSQL database. So that's, on the one hand, what are they afraid? On the other hand, it may cause you to waste a lot of time trying to learn a new system, depending on your team's skills. A good team should be able to learn a new thing, but it still may affect the choice that you make. So the key points of what we've learned so far. Key points of what we've said in this chapter. Software architecture is the fundamental organization of a system embodied in its components, the relationships to each other, and the environment, the principles guiding its design evolution. The architecture of a software system has a significant influence on non-functional system properties such as reliability. Right. What you're choosing in your architecture is going to affect how reliable, efficient, and secure your program is. Architectural design involves understanding the issues that are critical for your product and creating a system description that shows the components and the relationships. Okay, you have to show the relationships, and also you have to choose things. They choose the components that are good for your software. The principal role of the architectural description is to provide a basis. This is like, when we say architectural description, we mean like a diagram, a design of what the components are and how they relate to each other. Is to provide a basis for the development team to discuss the system organization. In other words, it's not necessarily the final opinion what you're designing, but at least it lets you all understand the same thing and see if you agree about it and understand it in the same way. Informal architectural designs are effective in architectural description because they are fast and easy to draw and share. System decomposition involves analyzing architectural components and representing, like, how do I get rid of this thing? Got this black thing here from Zoom. Oh, here we go. Okay. Analyzing architectural components and representing them as a set of finer grained components, right? And in other words, the next thing is you take your components and you make finer grained components. To minimize complexity, you should separate concerns, avoid functional duplication. Now, each function should be unique, and focus on component interfaces. Web-based systems often have a common layered structured, including user interfaces, application-specific layers, and a database layer. We saw that, those 3 layers. The distribution architecture in a system defines the organization of the servers in that system, the allocation of the components in that system. In other words, what servers you're going to have and what they're each going to do, and being service oriented in the sense that you have. We're going to talk more about that when we talk about microservices. But the point is that each server has its own, has jobs that it does, and you don't even view it in terms of servers. You view it in terms of services, and maybe you have that. We said we have that, pool manager, the web server, who you always address to him, and then he will get the actual service from another server, and that's a level of abstraction that allows you to change your servers, and how they're providing the service. Multi-tiered client server and server-oriented architecture (SOA) are the most commonly used architecture for web-based systems. In other words, the SOA has more layers. The server client is just 2. There's also peer-to-peer, right? I don't know why he doesn't mention that also here, but there's also peer-to-peer, where every client is also a server. Making decisions on technologies, database and cloud technology is an important part of the architecture design. Okay. Wonderful. We finished this chapter. See here, we're going to talk now about cloud-based software. And then there's microservice architecture. Okay, so let's talk about cloud-based software. So this is really, we already did talk about cloud-based, we're talking about a little bit more. I'm just gonna, wait a second, let me pause the recording and I want to get a glass of water. Okay, so now we're going to go deeper into cloud-based software. Let me go to the next slide there. Okay, so what is the cloud? The cloud is made up of a very large number of remote servers that are offered for rent. So this is what you're asking. You're saying, Sahava, you're asking, what is the cloud and how does it rent a server? So I guess we're going to talk about it more. So they basically rent by company, they rent the servers out. Okay, the cloud-based servers are virtual servers, which means that they are implemented in software rather than in hardware. Which is what I was telling you, that it could be a server that actually has many servers on it. We call them, in other words, essentially, it's really one very powerful server which has in it divided up many servers, which are in software. You can rent as many servers as you need, run your software on these servers, and make them available to your customers. In other words, they can host your website, which is very interesting because sometimes you have, like, let's say, some store that is selling pet food, on the internet. All it does is sell pet food on the internet. Now, Amazon also sells pet food. So you have a very bizarre circumstance where you can actually be a pet food store on the internet and you're renting your servers from Amazon and you're actually competing with Amazon. But Amazon's providing you the servers. And somehow Amazon is, impartial, or they don't know what you're doing, or even if they do know what you're doing, they are, not going to crash your servers. But it can become, as your company grows, it can become an issue that you don't want your servers to be on Amazon when Amazon is your competition. Although nowadays, I think everybody knows that they're not going to beat Amazon at their game. So, and Amazon is not. I mean, Amazon is. I don't know how Amazon is whether it feels threatened by other small companies, but in any case, it's sort of weird that you use Amazon. Sometimes people prefer Microsoft for that reason. That Microsoft is not in the business of selling, products on the internet. Okay, you can rent as many services. Your customers can access these servers from their own computers or other network devices such as tablet or even a TV. Cloud servers can, in other words, like Roku, could be running on Amazon servers. Cloud servers can be started up and shut down as demand changes. That's what I was saying. You have these scripts. Sometimes they're called chef scripts. Is one type. But basically, you have this. You tell Amazon, bring me up 10 servers, and then you run a script which does all kinds of commands to that server to get it up and running. So you very quickly can bring up a machine. You may rent a server and install your own software on it, or you may, that's what I was saying, you can rent the server and then you just get an empty machine, an empty virtual machine, and then you have to install everything. Or you may pay for access to the software products that are available in the cloud. You could say, I want a MySQL server, and Amazon will sell you a MySQL server already set up with no date, with you'll decide the password for this, and then you can make tables on it, you can delete tables on it, and it's your server. And you didn't have to, and they'll also do, whenever there's an update, they'll make sure it's updated. You can, if you tell them you want 2 servers and you say you want them to be mirrored so that there's, in case one crashes, I have the other one which also has the data, you know, they'll do that for you. And all you have, and you know, they provide you with whatever service you want. So what are the advantages of this? It gives 3 things here. I mean, it's just terminology: scalability, elasticity, and resilience. Scalability means, my definition of scalability is a little bit different. It's the same. Maintain performance as the load increases. Or another way of saying it, as I increase the number of servers, I increase the number of clients that I can deal with. Because you say, well, that's obvious. It's not always obvious. Sometimes there's a bottleneck. Sometimes just because I increased it, I don't get twice. I double the amount of servers. I don't get double the amount of ability to handle clients. Elasticity, adapt the server configuration to change demands, which also is provided. In other words, I can tell Amazon has experts, in server maintenance, so they'll be able to change my servers as I need. If I need all this, bigger disk, most simply, if I need a bigger disk, or if I need different software. And resilience, maintain service in the event of service failure. So let's talk about each one of these. Scalability, elasticity, and resilience. Scalability reflects the ability of your software to help increase the number of users, as we said. Elasticity is related to scalability, but it also allows for scaling down as well as scaling up. That is, you can monitor the demand of your application and add or remove servers dynamically as the number. So that's like scalability, but it's more elasticity that is up and down. You can go squeeze like a rubber band can go in and out. Whereas scalability usually just means as I increase, do I get better performance? Resilience means that you can design your software architecture to tolerate server failures. You can make several copies of your software concurrently available. If one of these fails, the other continues to provide a service. In other words, once you're renting, you can rent 10 servers, and you can one can be a backup. You don't, maybe you don't want to buy, maybe you don't have room in your office for 10 servers, but once you're on the cloud, you can have as many as you want. So you can have more resilience. Cost. So, there's a catch-22 because on the one hand, you avoid the initial capital cost of buying all the hardware. On the other hand, you have a monthly payment you have to pay. But these are the benefits. Startup time. You don't have to wait for the hardware to be delivered. You can start up, today, same day. The Amazon is ready for you. Server choice. If you find that the servers you are renting are not powerful enough, you can upgrade to more powerful systems. You can add servers for short-term requirements such as load testing. In other words, you may want to test your system where many people are trying to access at the same time, but you need other machines to do that. So you may want to set up other servers to be to masquerade as clients to approach your main server and ask for services and see how it handles them. In other words, that's called load testing. I want to see if my server can withstand millions of people asking for data. So, but how am I going to get those millions of people? I'll create another server that will make millions of requests a minute and see how my server does. But that other server, I don't need it forever. I just need it when I'm doing load testing. I'm not going to do load testing every day. If you have a distributed development team working from different locations, you can easily create a situation. You can easily give them all the same development environment. This is a big problem, even in companies that is a big problem in companies that work today, where you have different programmers in the office, and they have they're all using Microsoft. Let's say, for example, they're all using Microsoft Visual Studio to program. I'm just using that as an example because you're familiar with that. And let's say one of them, though, has the most updated version. Another one has a version from 2 weeks ago, or from a month ago, or from half a year ago. And he adds some new program, some lines of code, and it works great for him on his system. But when he puts it onto the repository of, where the actual code is the deployment code, it breaks the system. Why? Because the environment that he's working on is slightly different from the deployment environment. And that's because, he didn't bother to update something that he's supposed to update. Because each person is responsible for his own machine. But if I'm hiring from Amazon, if all my developers are working on a virtual environment being provided by Amazon, then Amazon is providing a uniform environment for all of them. So that's a huge advantage. That's a huge advantage. It's a big problem in companies. And it's a reason why your development should be remote, which, you're not going to use. I don't think that, I'm not sure about this, but I don't think that Visual Studios allows you to be remote, but certain environments do.
What do you mean by letting it be remote? Like being attached to GitHub?
No, I mean, like when you're in Visual Studio is installed on your computer. Imagine using Visual Studio where it's not installed on your computer. It's installed on a server, and you're just getting a screenshot. You're excuse me. You're like getting a forwarding of the screen from that computer, and you're working. It looks like it's on your computer because you have a screen and you can press the mouse, but everything is remote.
So is it like using like a website IDE, or it's different? Like something like Code Anywhere is a website, we could just do anything, but it's a website.
Yeah, I guess so. I
you
don't know that, but yeah, I guess, yeah, sounds right to me. In other words, I'm coding, and my code and the environment, when I press build, who is running my code? Is my local machine running my code, doing the build, or is the build being run by a server and let's say giving me the results? I mean, there's different ways of doing it. You could have a component, you could have it componentized. You could have like the build component is done there, When I run the program, is it running on my computer or is it running on the server? You can set up, for example, Notepad++, such that it's directly connected to another machine, a remote machine, and you're typing in Node++ on your computer, but every type that you type is actually updating, is being sent across to the cloud to some server in Kentucky. And when you and you're editing it, and when you press, and then you go to the window for compiling, when you press the compile button, it's compiling in Kentucky. Now, if all of your programmers are working like that, then they're all working on the same environment, because that environment is provided by someone else whose job it is to provide a uniform environment for all your workers. And the workers themselves don't have to worry about updating their software, because they're not using any, there's no software on their machine. All they have is an interface. Is that clear? Zahava?
Yeah.
Is that what you meant? Is that the way this thing that you're talking about works?
It's been a few years since I've used it, but it was used for like HTML and CSS, where you would, I don't know if it was shared. Maybe there's a possibility for it to be shared. You have to make an account. You could connect it to like Google Drive or something. So everything you write automatically saves there, and then you can just reopen files and then run it so that it runs, and then it shows you, it opens up with an HTML website.
Right. So it doesn't have to be, HTML is one way of doing it, but it doesn't have to be HTML. It can be smarter.
Right, it could have been any language, but in the class I was using it in, it was for HTML.
No, I mean the communication. How is the communication done? That we don't have to get into that. But how is the data being passed to the server in Kentucky? So it's obviously by a TCP/IP, but it may not be by HTML. It may be some other top layer. You learned about the 5 or 7 layers of ISO. You guys learned that? Yeah. If you didn't, you should, or you will in the future probably. Okay, so the benefit, wait, where is this where we are? Yeah. So the benefits of using the cloud is you avoid the initial costs. You don't have to wait for, you can get it from Amazon right away. If you find the servers you are renting are not powerful enough, you can upgrade to more powerful systems. You can add servers for short-term requirements such as load testing. We said that. If you have a distributed development team Right, so we said this. This is the idea that you can all work in the same development. The key word here is development environment. The same development environment. Virtual servers run, virtual cloud servers. Virtual servers run on an underlying physical computer and is made up of an operating system plus a set of software packages that provide the server functionality required. Right, it's a virtual server, there's a physical server underneath it, and then software on the server. Once you have the server running, then you can put software in. A virtual server is a standalone system that can run on any hardware in the cloud. So therefore, I can move it. If a particular hardware breaks, it can be moved to a different hardware. This run anywhere characteristic is possible because the virtual server has no external dependencies. Now, this is not dependent on the architecture of the machine that it's sitting on. Virtual machines run on physical server hardware can be used to implement virtual servers. I don't know if you know about VMware, but VMware is, I think we see a picture of it. A VMware is that there's a hypervisor or some kind of low-level operating system, which you then install on top of it. We talked about it in operating systems. And on top of that, you put different machines. And so those machines actually do, when I say machines, different as operating systems. Those higher level, those regular operating systems like Unix and Windows that are on the hypervisor, which is lower level, they only interact with the hypervisor. They never interact with the actual hardware. So therefore, they become independent of the hardware. This is what we call abstraction, which we use all the time in many of our courses, or the ones that I teach. That you abstract away from the underlying hardware, and that allows you to move the operating system to a different machine, and you're not dependent on the hardware. Here we say a hypervisor provides hardware emulation that simulates the operation of the underlying hardware. So in other words, I wish, is there a picture of it? Yeah, here we go. This is the picture you see. Here is the server. This is how the cloud works, essentially. Well, how does it work? Because we have a server hardware. That's the one very powerful machine. And then we have some kind of basic operating system that is put onto that machine. Nowadays, these two levels are combined, at least as far as I understand. Hypervisor, yeah, these are usually combined. So the host is whatever the host operating system is. Let's say is some special hardware, some special operating system, which then has a hypervisor on top of it. And the hypervisor, what it does is it allows me to install different operating systems. Here you see Linux, and here you see Windows. Here you see that it's a software, is like, for example, Outlook is running on top of it, and which is a specific Windows software. Outlook won't run on Linux. And then you have an Apache web server, which is specific web server for Linux machines. And this will be your virtual server. So if I want a Outlook server, Amazon will just create me one of these things, a guest operating system with Windows and Outlook. Or if I want an Apache web server, they'll just create me Linux, and it'll all be on top of this hypervisor. And if I want, I can add a third one or a fourth one or a fifth one, all on the same hardware. Until eventually, obviously, there's a certain limit. At a certain point, the machine is going to start slowing down because I put too many virtual machines on top of this machine. So, but that's not your problem, but that's a consideration. But the point is, that's how it works. This is how I'm able to put many different operating systems on top of one operating system. And this hypervisor acts as a kind of go-between, or an agent, or a, he is, if I have a certain request from the hardware, I request it from the hypervisor. I request it from my operating system. The hypervisor then receives that request. Now, the operating system thinks that the hypervisor is the hardware, so he makes the request to the hypervisor. But the hypervisor then goes to the hardware and provides the required service. That's how virtual machines work. I mean, exactly how the inner workings of a hypervisor. So you'll have, that's above my pay grade. That's that's, you have, that's a whole expertise on how that's done. It's a whole company. There's a company called VMware, which does that. Virtual machines running on physical servers can be used to implement virtual servers, as we said. If you use a virtual machine to implement virtual servers, you have exactly the same hardware platform as a physical server. In other words, this Linux or this Windows Server operating system thinks that it's on hardware. It doesn't have any, from his perspective, he's on the hardware. He doesn't notice this layer in between. Oh, container-based virtualization. Where is this? Yeah. If you are running a cloud-based system with many instances of applications or servers, these all use the same operating system. You can use a simpler virtualization technology called containers. And now I actually have a video I want to show you about containers. But before we do that, I'll talk about containers, and then we'll see the video. Although, yeah, so containers, the idea is like this, that you instead of having different, in other words, I could say like this. I could say, okay, I want a service, I want an Apache web server. So I'm going to put a Linux thing here and put a web server. But I also want a mail server to provide my own mail system. So I'm going to put another Linux operating system and put mail. I say, oh, wait a second, don't do that. Put them on the same Linux operating system. Because what are you going to do? A whole nother server just for the mail, and a whole other server for DNS, and a whole other server for every single feature is going to be on its own server. Put them all together. I say, but no, I don't want that. I want them on different servers. Why do I want them on different servers? Because what if the Apache one crashes the server? Something happens. I get some denial of service attack on my Apache website. So then all of a sudden, some attackers have brought down my website, and all of a sudden my database doesn't work because it's on the same machine. It's on the same virtual machine. So that's why I want my database to be on a different one. I want my mail and my DNS all to be on different servers so that they are, I don't know what's the word. They're sanitized. They are separated from each other so that what affects one won't affect the other, and I won't have like a domino effect where one thing goes down and then everything goes down. You understand this point? Students, do you understand this point? If everything is separated, then if I crash one, I don't crash all of them. Or if one overloads because too many people are coming to my website. Now, but it's annoying to have all these on different servers. So what's a better solution? If I could somehow keep them on the same operating system, all these different features, all these different services, like a web browser and a database, on the same operating system, but have the containment. We talk about containment in like the war in Afghanistan. If we could have the containment, if each one could be separated from each other so that nothing that happens to one will affect the other, well, then I may as well have them on the same operating system. The only reason I wanted different servers was because I didn't want a contamination. I didn't want one failing to contaminate another. But if I can contain them so they don't contaminate each other, then I don't. And as long as they're all running on the same operating system, if one is Windows and one is Linux, I can't do it. But if they're all on Linux or all on Windows, then and if I have some way of making an impenetrable wall between the services, then I may as well have them on the same operating system. And that's the idea of containers. That's why it's called containers. Containers means that I have containment. I have contained. I localize. I don't know what's the best, whatever. I have containment and I don't have contamination. I like that word. I don't have contaminant. One does not affect the other. If you are running, so this only works where you have the same operating system. Using containers accelerates the process of deploying virtual servers on the cloud because I don't need to start up a whole new server. I just need to add a service. I just need to add a container. Containers are usually megabytes in size, whereas virtual machines are gigabytes. In other words, those different servers on the machines, each one is going to be a whole operating system. So that could be gigabytes of data to have a whole operating system. Now it's not a whole operating system, it's just the service that I want. And it'll be megabytes. Containers can be started and shut down in a few seconds rather than a few minutes. Containers are an operating system virtualization technology that allows independent servers to share a single operating system. They are particularly useful for providing isolated, they're using the isolated, or I was saying contained, isolated application services where each user sees their own version of an application. That's also true. If I want, like somebody to have administrator version of a certain website and somebody to have the regular version, so I can use containers. So only in this container do you get administration rights. So now we don't have a hypervisor anymore. We have the host operating system, and then we have some kind of container manager, which is going to manage these different containers for me, which are all running on the same operating system, not different operating. Notice there's no, it doesn't say Linux and Microsoft here. Everything is Linux or everything is Microsoft. There's just one operating system. And then we have each one comes with its own server software and application software. And here we're showing that different users can use them. But I say even if the same user uses both of them, the point is that I avoid that domino effect because I've isolated them. But he's talking about a different use, which is like that different users want different purposes, have different purposes to have isolated services. Like I said, the example of, well, here, what's their example? Graphic design software, graphic design software. What's the difference? This is actually the same services, so I don't see the point of this example. But imagine one would be doing something that only the administrator could do. So Docker is an example of a container software. You may have heard the term Docker. Has anyone heard that term? No, you should. Well, this is, we're talking, if you're ever curious about the field called DevOps, so this is a major aspect of DevOps. Again, this is not programming, but remember, we're learning architecture. We're learning, so we're talking now about systems, how to create systems. And Docker containers were developed by Google around 2007, but containers became mainstream only in 2015. An open source project called Docker provided a standard means of container management. Now, as we're talking about this layer here, this container management, how to build such a thing, and that it should be easy for me to make a container. Docker is a container that allows users to define the software to be included in the container as a Docker image. In other words, this will be an image. What is an image? An image is like a single file of data that I can load onto a machine, and then I have all the services that I want, like a compiled program. It also includes a runtime system that can create and manage containers using these Docker images. Well, I'm going to skip this. I'm going to skip exactly how a Docker runs. Not that important. I mean, it is important, but it could change. So let's just do this. Right, Docker images. Once you have this Docker image, it's like a simple file. So you could share it and run it on different hosts. You could say, here's the Docker for my programmers. All my programmers who want to program for my software, you use this image, and they'll essentially get a version of the operating system that I want them to use. Everything that is needed to run a software system, binaries, libraries, system tools, is included in the directory. A Docker image is a base layer, usually taken to the Docker registry, all right, with your own software and data added as a layer. You don't need to understand that, but the idea is that I have a single file, which is an image. An image is always a single file. And I run that image on my Docker host, and now I have the environment that I want my worker to use. So I create an image for all my programmers, for all my QA people, quality assurance people. To change an application, all you have to do is to ship the changes that you have made to its image. Just a small, in other words, you can incrementally change the image once it's installed. So what are the benefits of containers? They solve the problem of software dependencies. You don't have to worry about the libraries. And so, you know, I want to wait. Let's take a break here, and I will. Let me stop the recording or pause the. Yeah, I'll stop the recording.